Good morning, everyone. My name is Mariana Laino, and today I'm presenting the work in orbit manufacturing and recycling of solar power satellites. A solar power satellite is a system designed to capture solar energy in space and transmit it wirelessly to a receiver on Earth. Space-based solar power provides a constant source of clean energy, being unaffected by atmospheric conditions and the day and night cycles, and it contributes to climate change mitigation for these reasons. The concept, though, faces significant challenges. To meet Earth's energy requirements, the collecting areas must be large to maximize the solar energy harvesting. Due to costs and volume constraints of the launch vehicle fairings, they cannot be launched as single units, but they must be assembled in orbit. In this case, they can be manufactured in either on Earth or in space. Furthermore, they are expected to operate for several decades and demand regular maintenance and the replacement of faulty components. At the end of their life, the creation of new debris should be prevented, meaning it's desirable to remanufacture and recycle the components of the SPS. This project envisions a circular space economy, as illustrated in Figure 2. In this framework, the modules of an SPS are manufactured in a recycling station in orbit using the material already available in space, like debris, module of defunct satellites, or even lunar resources. These modules are transported to their operational orbits using natural dynamics and controlled maneuvers. Then, a swarm of servicing satellites assembles the modules into a functional solar power satellite. The same servicing satellites handle the maintenance to ensure long term operations and dismantle the satellite at the end of life. And the components are then transferred to a recycling station to be repurposed and recycled. This work deals with problems related to circular space economy and to the recycling of solar power satellites. In particular, it deals with the efficient transport of material and the assembly and disassembly in orbit. So, in the context of in space manufacturing and recycling, it's important to collect non active objects from their orbits and transfer them to a recycling station where they can be stored for future use or immediately repurposed to build new space systems. In this case, it is necessary to identify the most populated regions in Earth orbit and, more in general, in cislunar space, where the needed material can be transferred to the desired location. These regions can function as hubs within a larger transport network, all connected to a central recycling station. In this work, the transport network connects LEO and Moon Halo orbits with a station located in a geosynchronous orbit or GSO. The idea proposed here is to map regions in the phase space where natural dynamics plays in favor of the transfer and to identify pathways to reduce propellant budget and to facilitate in-orbit construction. For transfer from the low Earth orbit to geosynchronous orbit, we exploit the Sun and the Moon's perturbations to modify the orbital elements, reducing the propellant needs. The schematics in the figure illustrates the key phases of this transfer method, which mainly consists in increasing the apogee of the transfer orbit and propagating it for enough time to leverage perturbations, and then in finding the points where it's more convenient to perform the maneuvers. Systematic scans of departure times and orbital elements were conducted to find combinations that resulted in significant cost savings with respect to direct transfers, achieving up to 30% delta V reduction at the expenses of longer transfer times. For transfers from the lunar region to the GSO, we use environmental structures, which are structures created by the gravitational influences of the Earth, the Moon, and the Sun, to reduce propellant consumption. The schematic illustrates the key phases of this transfer method, which are the injection into a manifold departing from an L2 Earth Moon Halo orbit, and then into an Earth bound optimal trajectory. Schematics, again, systematic scans were conducted across the departure dates and across halo orbit parameters, and they revealed significant cost savings compared to direct moon transfers with a minimum delta V cost of 1.1 kilometer per second. Another important thing is to find the optimal location for a recycling station. to ensure efficient and sustainable operations. Up to now, we have the hypothesis was that the recycling station was in GSO, but this region is dangerously close to protected regions. So in this case, we identified some other locations for a possible recycling station. We identified in particular optimal orbits to minimize the maneuver cost and to maximize the accessibility from regions like Geo, Leo, and the Moon. Um, we used perturbation assisted transfers, similar to the ones seen previously, and we did a mapping of the potential orbits based on long term stability. At the end of this process, we found good candidate orbits around 100,000 kilometer radius, 20 degrees of inclination, and right ascension of ascending node spanning from minus 40 to 40 degrees, and that were stable for over 50 years. I forgot to mention that these orbits are circular, of course. These orbits offer cost-effective material transport and savings up to 25% in delta V compared to direct transfers. In the figure, you can see some of these candidate orbits with the associated delta V costs from each key region. Then, a model for analyzing the dynamics of the satellite during nominal operations and during the assembly and disassembly and the replacement of the components is presented. The orbital motion of the satellite is described by a perturbed two-body problem, where the main perturbations, like the solar radiation pressure, were considered. The rotational motion is described by Euler's equations, and all the external torques applied on the satellite are considered. Um, Most importantly, a simplified model is used to characterize the assembly and disassembly process. It is assumed that the elements are removed one by one, and when this happens, a small impulse is applied to the structure, and at each of these steps, the new mass distribution, inertia tensor, and surface area is computed. Um, the model was applied to SPS alpha case study that you can see in the figure, and simulations were conducted to assess the effects of adding or removing reflectors, applying small impulses with random directions. The figure shows the result of a Monte Carlo analysis run with 1,000 cases, and here the attitude angles remain bounded throughout the whole process. So the dynamic behavior of a structure during the construction process is highly dependent on the sequence in which the modules are integrated. So identifying an optimal assembly sequence is essential to ensure safety and stability during the process and also to minimize the dynamic response. The case study in particular is a large diameter flat antenna structure that is composed of square subpanels and is assembled in geo. Two robotic arms add two subpanels at a time, applying small impulses on the satellite. An optimization problem is solved with the objective of minimizing the attitude angles during the process by selecting the optimal subpanels to be integrated each assembly operation. All this was done while imposing some constraints on the realizability, repeatability, and continuity of the operation, which mean that we're making sure that the operation is physically feasible. The optimization is conducted using a genetic algorithm, and a number of um, different simulations were run. The simulations were explored different initial dates, insertion directions, and impulse magnitudes. Multiple rounds of the genetic algorithm provide many optimized sequences. The results show that when the impulse is small and the sequence proceeds symmetrically, starting from the center and proceeding outwards, the attitude angles have a small amplitude and are bounded. An optimal assembly sequence with the associated evolution of the attitude angles are shown in the figures below. To conclude, this work presents innovative solutions for challenges associated to in-orbit manufacturing, assembly, and recycling of solar power satellites, aiming at achieving a circular space economy. A future analysis will conduct a life cycle sustainability assessment on a self-sustaining SPS system to better understand the actual environmental impact of the concept and of a circular space economy in general. Thank you for the attention, and if you have any question, please don't hesitate to contact me. Thank you.